Now we're going to move away from specific types of relations and look at some operations that you can do on almost any type of relation. In particular, we're going to look at the operation of composition of relations. So we're going to review composition of functions, which is something that you learned back in your algebra days. We're going to use our understanding of how composition of functions works to help define what composition of relations works. It's going to be very similar. And then we're going to show an example about how this works. All right, so I want you to recall from your algebra days how we take the composition of two functions. So what we have is we have two functions f and g, and when we combine them, the notation we use to talk about the composition of functions is g circle f. So you may recognize that notation a little bit. And the idea is g circle f is the function that takes an input x, and what you do is you output g of f of x. So that may look a little bit abstract, but let's make it a little bit visual, right? So if we think of functions as operations that take inputs to outputs, so what we do with the composition of functions is we start with x, and then we do f to it, and when we do that, we get f of x. That's what that arrow means. We start with x. The f takes x along the arrow and transforms it into f of x. And then what we do for g circle f of x is we take that f of x, and then we do g to that. So we start with f of x. G transforms f of x into g of f of x. So it's a two-step process. X goes to f of x, and then g goes to g of x. F goes first, g goes second, and that may seem a little bit weird. The g is written first and the f is written second, but because of how we write our function notation, it makes more sense to write them in the reverse order that we actually do the functions. And to be honest, that's something that's going to come up with composition of relations as well, so we may as well get used to that right now. All right, so I want to make two important points about the composition of functions. First of all, notice that we're using arrows here, and if that looks familiar, it's exactly what we've been doing for relations. Remember, the directed graph model of relations is one of the ways that we visualized relations. And what we're doing here with these arrows is we're using arrows to visualize functions as relations. And so what we do with functions, we can maybe do with relations more generally. And the second thing to notice is that when we have the arrows drawn, to get from the first element, that is the input, to the last element, which is the last output, we have to travel along two consecutive arrows. So we start at one element, travel along an arrow in the right direction to another element, and then start at that element, travel along an arrow in the correct direction to a third element to figure out what your final element is. So now what I want to do is apply this same sort of reasoning to relations. So I'm going to have R, that's a relation between the set A and the set B, and then I'm going to let S be a relationship between sets B and C, and as we will see in a little bit, it's really important that the second set of the first relation is the same as the first set of the second relation to make that connection. And we're going to define the relation S circle R between the sets A and C. So that means when we do the relation, the first element in the relation is going to be from A, and the second element of the relation is going to come from C. So when do we have A related to C under this relation S circle R? And again, remember, the A on the left is in A, and the C on the right is in C. Well, we're going to play the same arrow game as we played before. We're going to start with A. We're going to try to find some element B where we do R, where A and B are related under the relation R. And then we're going to try to find an arrow from B to C where B and C are related under the relation S. And if that two-arrow system works out, then A is related to C. So another way of saying that is there exists some little b in B such that A is related to B under R and B is related to C under S. So here's our formal definition. So let R be a relation between the sets A and B, and let S be a relation between the sets B and C. We define the relation S circle R between the sets A and C as follows. We say that A and C are related under S circle R when there exists some little b in B such that A is related to B under R and B is related to C under S. So let's look at this in an example. If we can define relations R and S on the set of real numbers as follows. So everything is real numbers in this one that we're relating. So A is related to B means that A minus B is an integer, right? So that's something that that's a relation we've seen before. And we're going to define C related to D under S when if we look at C minus D, that gives us an integer that is congruent to 1 mod 4. And just keep in mind that C and D themselves don't have to be integers. They just have to be numbers where when you subtract them, you do get an integer. So let's find some pairs of numbers that are related under the relation S circle R. So we want to start with R, right? R is on the right, S is on the left. That means R comes first, S comes second, right? So we're going to start with 5. And note that that's related to 7 because when we take 5 minus 7, that is the integer -2. So as long as that's an integer, that means they're related under R. Now I want to find something that's related to 7 under S, which means when I subtract 7 minus that number, I get something that's congruent to 1 mod 4. And it turns out 2 is the perfect number to do because 7 minus 2 is equal to 5, and 5 is congruent to 1 mod 4. So we have 5R7, we have 7S2, and when we combine those to see which ones are related under S circle R, that means that 5 is related to 2 under the relation S circle R. And again, as I mentioned before, we don't have to do just whole numbers or integers. Notice that 1/2 is related to 5/2 under R, because if I take 1/2 minus 5/2, that gives me what? -4/2, which is -2. -2 is an integer. So those are related under R. And if you look at 5/2 and -5/2, those are related under S. That was a little more tricky. If you take 5/2 minus a -5/2, you got to cancel those negatives. You end up with 10/2, which is 5. 5 is congruent to 1 mod 4, so those are related under S. And therefore, if you're looking at S circle R, you take the first one on the left, that's the 1/2, the last one on the right, the -5/2, and that tells you that 1/2 is related to -5/2 under the relation S circle R. Kind of sneaky, but that's the way it goes. All right, so let's look at the same relations R and S that we had before. R is A and B are related when A minus B is an integer, and C and D are related under S when C minus D is congruent to 1 mod 4. And I want to ask a much more general question. This is going to be a little tougher, so we'll have to do a little more work. What are all the numbers that are related to 1/2 under S circle R? That's a tough one because they're probably going to be infinitely many. So let's take a shot at it. Well, here's what we need in order to do this. We need 1/2 to be related under R to some number B, and then that same number B to be related under S to some other number C. And the thing we're looking for here is we want the C, right? 1/2, if we have that thing set up, then 1/2 is related to C, and that's exactly what we're looking for. Well, let's just take one step at a time and see if we can sort of solve for C, if that makes sense. So let's start with the first one. We know 1/2 is related to B under R, and what that means is when I subtract those two, I should get an integer. So that says that 1/2 minus B is equal to some K, where K is an integer. All right, so far so good. I don't know what the heck's going on with C, but that at least tells me what I have to have going on between 1/2 and B. So if I solve for B in this equation, which is going to be helpful down the line, I get B equals 1/2 minus K. And so we'll see how that's going to be useful later on. Now I'm going to look at the second one. The second one says that B is related to C under S. And you may have saying, well, where's the B? Well, remember, B is equal to 1/2 minus K. So I'm going to replace that B with 1/2 minus K, which tells us that 1/2 minus K is related to C under S. And what that means is when we subtract those two, 1/2 minus K minus C, that gives me an integer that is congruent to 1 mod 4. And boy, that's gonna be a real piece of work there. But we'll do the best we can. What does that mean to be congruent to 1 mod 4? Well, that means that 1/2 minus K minus C is going to be 1 plus some 4 times some integer. Right? So M is going to be an integer here. So now we're going to solve for C. Remember, C is what we're really interested in. K could be anything, any integer, right? M could be any integer as far as we know. We want to solve for C to see what all the possible numbers that we can get for C. Well, when we do that, we get negative 1/2 minus K minus 4M. And so what numbers do we expect to get? Well, K is an integer, could be any integer, literally any integer. M could be literally any integer. When we subtract those two, the negative K and the negative 4M, that could give us any integer as well. So that negative K minus 4M could be anti-integer n. So C is always going to be negative 1/2 plus n for some integer n. Now I said it could be any integer. Could it literally be any integer? So if n was some random integer that we just chose out of the blue, do we know that we could somehow write it as negative K minus 4M for some integers K and M? Well, it turns out we can if we're clever enough. So n is some integer. If we let K be negative n and we let M equal 0, then that means negative K minus 4M, then negative K minus 4M is literally going to equal n. So we could literally get any integer we want. So not only does C have to be negative 1/2 plus an integer, but negative 1/2 plus an integer can be engineered to be solved for C. So that tells us that C is equal to negative 1/2 plus n for any integer n in Z. And that means, remember, our whole goal in the beginning was what is 1/2 related to under S circle R? Well, 1/2 is related to C under S circle R precisely when C is equal to negative 1/2 plus n, where n is an integer. All right, so now I want you to try to work on the activities for composition of relations. That's on the PDF file included with this video.